Vem com a gente! Nós somos um time feito de pesquisadores e de pessoas com deficiência.
Siamo in competizione l'uno con l'altro.
우리는 흔들리지 않는 신념으로
Wir teilen Emotionen, Spaß und eine gemeinsame Vision.
Wir stehen für Inklusion und Diversität.
모두에게 주어지는 동등한 기회와 권리.
우리는 그 당연한 진리를 지지합니다.
Pari diritti e pari opportunità per tutti.
Für mich persönlich ist CYBATHLON bis heute die Erfahrung meines Lebens.
Es ist der Sieg!
Wer Teil vom CYBATHLON?
Porque através do CYBATHLON você pode melhorar a sua vida e melhorar a vida de outras pessoas através do seu exemplo. Junte-se a nós!
Mach mit! Werd Teil vom CYBATHLON 2024.
I would like to welcome you to the third CYBATHLON lecture of this fall. I would like to welcome our audience here in Zurich, as well as our audience all over the world that joined us today. I'm Julia Amos. I'm the Head of Discipline of the Vision Assistance Race at CYBATHLON. Teams all over the world are currently preparing for CYBATHLON 2024, which will take place next October. On the road to CYBATHLON 2024, we, the team at CYBATHLON, are organizing different events for our community. One of them is the CYBATHLON lecture series. We asked our current CYBATHLON teams, as well as potential future teams, what topics they would be interested in. For these topics, we organized speakers that are holding lectures here in Zurich, like the one you are attending today. In the past couple of weeks, we already had 2 CYBATHLON lectures. In case you missed them and would like to rewatch them, you can access them on our website. Today, we are very happy to welcome 2 experts on user-centered design and technology transfer. Jan Meyer and Max Erick Busse-Grawitz will tell us more about how to bridge a gap between user-centered design and technological implementations. Before we start with the lecture, I would like to remind our users, our audience online, that they can use the Q&A function on Zoom to ask questions. We will later address these questions with our experts and hope to answer them well. With that, I would like to thank you again for being here today, and I will pass on the word to Jan for the first lecture. Thank you.
Thank you very much, Julia. Hello. Today we want to talk about how to bridge the gap between human-centered design and technological implementation. And for this, we of course first have to understand what is human-centered design actually. So, recapping a bit into my personal situation, I have been very interested in advanced assistive technologies from, even already in bachelor's and master's. And I've seen technologies all around the world, also, of course, at ETH, that look fantastic. You see people with disabilities getting a functional advantage out of them. And of course, at the CYBATHLON being showcased. But looking a bit into more deeper into the topic, we realize that there is an extremely largely unfulfilled potential of advanced assistive technologies due to missing availability and accessibility. And that means that there are not enough devices on the market, simply said. Why is that? We believe that main limiting factor of this missing availability and accessibility is actually the fact that the technology acceptance of these devices is still rather low. And also once they are deployed, there's a high chance of abandonment because the devices unfortunately have an inadequate daily life usability in a lot of cases. So this was something we had to look into. And funny enough, this was actually exactly how I got into the topic of user-centered design, because the inadequate usability of a device that participated at CYBATHLON in 2016 is the reason why I stand here today. The Varileg lower limb exoskeleton performed at the CYBATHLON 2016 with 2 pilots. And even though the performance was very good, the device ran smoothly, it was a beautiful experience for everyone, research wanted to continue on the device. And for this, we needed the pilots to come back into the lab and perform studies with us. Now then, they said, well, listen, the device was okay for the CYBATHLON. It was an amazing experience. But if you want me to come back and use this on a daily level or weekly, you really need to improve it, you need to personalize it, and it needs to be more comfortable for me personally. So you can see that using a device for a short matter of time, for a matter of competition, is something else than using it over a long period of time. And my challenge in that part, this was my master thesis actually, was to improve the physical attachment system. So how the pilot is attached to the device. And for this, I try to follow a very simple mantra. Frank Chimero actually has a good quote on the fact that people simply ignore design that ignores people. But what does that mean? It means that when you think about it logically, you can never develop a technology without the people that it is designed for. Right? And for me, it felt quite natural to try and develop a new physical attachment system together with the target users. That meant, first of all, understanding what the problem really was, instead of already trying to go for a solution. So I really tried to understand what's the issue with the current solution. So we evaluated on a subjective level together with the target users, plus, of course, some people who can also tell a bit more about uncomfortable zones below, let's say, the injury level of spinal cord injuries. We then had a lot of co-creative sessions together with those two users to understand how they would design it. They might not have the technical abilities at hand, but they surely have great ideas. And that's what we did. So together with the people with disabilities and together with the clinicians, we started ideating. Then we came up with a few concepts. Of course, nowadays you can do rapid prototyping with 3D printing. And in all these steps, we always went back to the target users and to the stakeholders. And we asked them about their feedback, and we kept iterating. And we actually did this not only once, but several times, such that we eventually ended up with an improved physical attachment system. That was to the large satisfaction of those target users, because we were able to customize it, to listen to them, and to improve it. Now, what we did there was actually the core of human-centered design. And if we look at human-centered design and simplify it a bit, it starts by empathizing your target users. That means, again, before you go in and think about how to solve the problem, you first have to understand the problem. And who better knows the problem than your target users? Once you have the wide problem space, you also need to define what areas of that problem space you want to address, because surely you cannot solve everything at once. So you have to go in and define your specific specs, your specific areas that you want to improve. And in terms of CYBATHLON, this, for example, means, do you want to be able to solve all the obstacles, or do you maybe want to be able to solve only a part of the obstacles, but on a very high quality? Right? That is a pure definition of your functionalities, and also depends, of course, on your target users. You then go about and ideate, create concepts, you of course prototype them, and eventually you evaluate them, as you just saw on the example before. And the more you do this, the more you increase the technology maturity, and you actually have to give yourself enough time to perform these iterations. Because it is very unlikely that in the very first try, on your first iteration, you will be able to solve the problem fully. So very likely in the first evaluation phase, you will realize you have to go back and start. And this is actually a continuously iterative process. Now, it seems quite simple, right? If I show you these phases, it all sounds very logical. But if user-centered design is that simple, how come then assistive technologies are often too complex and too complicated for daily life? Well, this question we wanted to specifically look at the CYBATHLON. Because the CYBATHLON offers the perfect platform to investigate the current development practices and also the success of these of advanced assistive technologies. If we look at it a bit objectively, what does the CYBATHLON offer in that terms? We have target users who are essential to the teams. Without pilots, there will be no participation at the CYBATHLON. We have task-based races and disciplines that resemble activities of daily living. So we have daily life relevance. And of course, we have inclusion, diversity, and innovation as main drivers. And this per se gave us the perfect platform at the CYBATHLON 2020 to actually access those teams and to ask them how they develop technologies and how satisfied the pilots are about these technologies. So what we did is we launched an online survey in order to try and challenge the premises of CYBATHLON. We offered the survey in 9 different languages because CYBATHLON is a global competition. So therefore, we also had survey versions in Korean, Brazilian, Portuguese, of course, French, Italian, and so on. What we wanted to understand is not only the pilot side, but also related to the technical lead side. And with technical lead, we included everyone that was involved in the technology. Also, some of them were more the project managers, but some of them were the lead engineers. We collected the data via Zoom prior to the races, so before any performance happened, right? I could not be yet disappointed or super happy about the performance. And eventually we were able to talk to 81 people. From that, 35 pilots and 46 technical leads. And now we can look into different interesting things. First of all, we can see that, I'm not sure if this is working, yes. We can see that from those 35 pilots, everyone except 5 were to some extent involved. That means 85% of the pilots that we introduced, surveyed, are involved in their device development. That's a good number already. And if you look into the reasons why some of the pilots were not involved, they were either using a commercial product, so there was not much more development happening, or they were not yet around at the time. That could also mean that there was another pilot in the same team that was around, and then they joined as a second pilot. And we had only one guy that said, well, I'm not a developer, I'm a pilot, so why should I be involved, right? But that number was interestingly low, so we can assume that most pilots are involved in the design, which means that user-centered design is happening to some extent or the other. But then we also wanted to look into those phases. So we have those 5 phases of human-centered design again here at the bottom, starting with empathize, and then going into evaluate. And what we can see is in red, we have the technical leads. Their involvement is basically always leading. In dark blue, we have the pilots. And in light blue, we have the opinion of the technical leads about the pilot's involvement. And what you can see is that actually the pilot and the opinion of the technical lead about the pilot's involvement is very similar. So they are fully aware of what's happening. And what we can see is that in the empathizing and in the testing phase, pilots are involved, so understanding the problem and then testing if you solved it, but not necessarily in those technical phases when we come into the solution space. That means we have to keep an eye on the fact that we have to keep a human-centered focus in the technological implementation. And Max Erick is going to talk about that in the second part of this lecture in more depth. We also then looked into the qualitative aspect of their involvement, and we asked the pilots if they felt like they were an active contributor in the development. And here again, we have 3 different statements. Statement A, the pilots mentioned if they felt like they gave active input on the development. And you can see that more than half of the pilots agree, but nevertheless, the technical leads overestimate the amount of active input that the pilot gave. So not all the pilots were fully satisfied with their active input. Also, if you look at statement B, we have the fact that if the inputs were then actually considered, and here the agreement even goes further away from each other, which means that, well, the pilots give somehow inputs in this empathizing phase or in the evaluation phase, but maybe it's not really considered. Right? Interestingly, if we asked if the pilots felt like they were involved sufficiently, they felt like this was the case to a very large extent. Right? So this is a very high level of agreement. So we can see that being involved, it does not necessarily mean you are part of all of the phases of development. It really is about the quality and the time you spend within those different development phases. One thing we also looked at was the sheer usability of these devices. And the main indicator of usability, one might say, is it being used or not in daily life? And we can see that right now, actually, only a minority of devices that participated at the CYBATHLON can actually be used in daily life or are being used. If you look at the reasons on the right side, we can see that the main reasons for this is, again, limited accessibility and availability. So the devices are not yet commercial, a lot of them, so they cannot take them home. But also they might be too big, too bulky, and they cannot really go into the homes of the people. And if we then separate these accessibility and adoption hurdles from usability limitations, we can see that comfort, overcomplicated use, and the necessity of support are limiting factors for daily life usability. So there are a couple of things we can do about those 3 points, right, when we are in development. Another thing that was actually quite interesting after the race has happened is we can understand, okay, now we talked to those teams before the CYBATHLON participation, now they participated and they reached a certain rank. And of course, we know participating at the CYBATHLON, anything can happen. You can have a very, very perfect device. There can be a technical issue. I don't know, the pilot can fall sick. Anything can happen. So not necessarily the rank performance tells us the whole story, but still we try to map out which user-centered design factors might influence the performance. So we looked at the relative ranks of those teams, and we can see that, for example, those pilots that use their devices in daily life generally perform better. Also, we can see that the longer the pilots were involved, the better the rank. So there are definitely some human-centered design factors that positively influence CYBATHLON performance. Also, in a follow-up study from the CYBATHLON team, actually, they looked into, for example, actuated degrees of freedom and also the weight of the devices. And again, you can see the more lightweight the device, the better the performance. For those having less degrees of freedom, better performance. And for those who followed CYBATHLON 2016 and 2020, know that surprisingly, oftentimes on the podium, there are some devices that are very technologically simple. So the question is, why do we then need complex devices? And I think that's something the CYBATHLON, tries to provoke out of the teams every day by every year or every edition, by making the obstacles more and more daily life related to really understand what exactly is the technological complexity that we need and how simple can we make it such that they have success. Another interesting factor is, for example, if you look at how the devices are being controlled. A lot of people outside of the field believe that the devices are mostly steered with brain-computer interfaces or complicated EMG control mechanisms. But 71% of all devices were actually controlled with buttons and joysticks. Why? Because it's simple, it's robust, and you can learn it very easily. Right? All of these things show us that the performance at the CYBATHLON actually relates back to human-centered design and to device usability. Now, looking at, let's say, how the devices are being developed, we also have to understand a bit what happens in the future and what happens actually in the field. And we started realizing, and as the CYBATHLON realized, actually, we always have a lot of teams who reach from research prototypes into then reaching a certain stage where maybe they even come into being a product eventually, right? So how can the CYBATHLON actually support this translation? And here, just really quickly, I want to introduce the technology readiness levels. It's a bit of a complicated scale. We don't have to go through all the different levels, but essentially, you're talking about technology being ready from basic research and concepts being established to basically being fully commercially available. And in between, you have different levels depending on your readiness. For example, the technology is being tested in the lab, or in an intended environment, or demonstrated in an intended environment, etc. And we looked into this technology readiness levels in the field of wearable robotics specifically, and we found something quite interesting. So from 150 investigated devices, we can see that a lot of them are stuck somewhere at the beginning of this prototyping phase. So they are still in the lab, being tested in the lab, but they can barely make the change to being in an environment where it's more meaningful and more demonstrative for daily life use. So apparently there is a translational gap happening somewhere here. If we look at what technological readiness level the CYBATHLON actually demands, we can see, and I think it could be a long discussion with the CYBATHLON team, which technological readiness level that is being required. But we can see it's maybe somewhere 5 or 6, depending how applicable actually the tasks and the race disciplines are, right? And if we map that into our other study, you can see that very likely a lot of or most of the teams at the CYBATHLON already made the jump over that critical hurdle, right? And this is quite interesting because there is potential then to move forward and to drive this into commercialization, or of course more applied research for that matter. You don't necessarily have to commercialize, but it's more about applied research. So this is the first thing that we realize when we map CYBATHLON teams onto, let's say, the industry benchmark. Then we have another very interesting insight from all the studies we performed, and bear with me for this graph here. I'm just going to introduce it to you. So on the x-axis, on the horizontal axis, you again have the technological readiness levels. And on the y-axis, you have the number of target users, or the number of users being involved. And in green, you have target users. So for assistive or therapeutic robotic technology, it's people with disabilities. For industrial augmentation applications, it's maybe people working in the baggage handling industry, right? So it does not necessarily have to mean all of them are people with disabilities. But now let's look at the fact that also a lot of teams, of course, test with mock users. So either neurologically intact volunteers in the case of CYBATHLON teams, or just the people who develop it and the colleagues left and right. And we can see, of course, in the beginning, so if you look at the red bubbles, this is much more important that you have some mock users that are also testing your device. And then the more you advance into commercialization, of course, this becomes less relevant because you want to test with your actual users. And if you look at the actual target users, this should steadily increase with your technology maturity because you need to understand if it also applies to other people. Okay? So understanding this graph now, what we can do again is we can map CYBATHLON teams. And if we map the CYBATHLON teams, we can see they actually have a bit of a head start to the industry or to the benchmark of let's say, all the other developments right now, because they start off with at least one pilot from the start. Many of the teams start off with 2 or even more pilots, or some also other people with disabilities on advisory boards, etc. So clearly there is a head start, right? But if they only rely on these teams and they come into this, let's say, competitionally required technology readiness level, what they have to make sure in order to advance is to keep involving more users. Because if you keep being down here and just focusing on 1 or 2 users, you're probably not being able to really go further in your technology maturity. This is something I think very important to consider what happens after CYBATHLON participation, or maybe between 2020 or 2024. So now if we look back with one of those studies, we obviously wanted to challenge the premises of the CYBATHLON. And the CYBATHLON platform has a couple of points that they hope to bring into the community. And one of them is to consider needs of people with disabilities. And we can see Well, pilots are being involved, human-centered design is happening, so clearly the needs are being considered. But again, we can see that maybe not all of those needs are directly implemented, right? Identifying chances and limitations is also very well visible because we can see the teams participate in the CYBATHLON. Not all of the teams can perform all of the tasks, and also some of the devices are a bit larger. Some of the devices, maybe even break down. So clearly, while showing the innovation and while showing the advances, we can also see the limitations of those still. And understanding what we just looked at today is also that there are still challenges ahead, right, if you want to move forward with your technology maturity. And lastly, promoting inclusion. I think this is a very easy one because, interestingly, when talking to all these different teams around the world, what we heard a lot from both sides, so from the developers as well as from the technology leads, is the fact that due to the CYBATHLON, it was the first time those two parties even interacted with each other. And it may be that some of them were developing advanced assistive technologies for years before, right? So clearly, in terms of promoting inclusion, the CYBATHLON definitely reaches that goal. Now, if you look at this translational gap, and I think this is an interesting aspect because also what Max Erick is going to look at in terms of technological implementation. We have to understand that there is a certain translational gap between basic research that is being funded from academia, from government, from the NGO sectors, and then real-life applications, which often means you have to privatize, you have to commercialize, and you need a product. And in order to move forward in the field, right, in order to have more technology on the market, in order to have higher usability devices, we need more projects to make that jump in the translational gap. And we can understand that a couple of interesting hurdles are actually being supported by the CYBATHLON. One, human-centered design, which obviously helps bridging that gap, is being supported by the CYBATHLON because the teams have to take the time and have to make the resources to involve pilots. In a usual academic setting, you don't have to. You should, but you don't have to. Also, the availability of target users is very often limited and also somehow restricted due to some medical or ethical regulations. So again, here, the CYBATHLON has established a concept and, let's say, a fast-forward framework that allows users to reach out to pilots, right? It's also a bit of a building of trust between people with disabilities and technology developers. So I believe that there's a very fair chance that CYBATHLON is somewhere in between here, doing a good job in bridging those two streams. Now, another thing that is very important that I talked a bit about today is the fact that just because you involve users doesn't mean you also do it right, and that you can really generate the involvement you want to achieve. And with this, I really mean the depth, the quality, and the impact of your user involvement. And a lot of this relates back to how you collect feedback and how you involve your target users. And here, together with the Relab, we created a platform to enhance human-centered design practices by optimizing the involvement processes. More specifically, how you empathize with the users, how you co-design with users, and how you evaluate your devices on a fair basis. So on the usability toolbox, and you see the URL down here, you have a wiki with different terminologies to get to know all those different terms I've been throwing around for half an hour now. Also, you have a lot of tricks and tips and tricks. You have a database with around 150 user research methods. So there is more to user evaluation than just interviews or a couple of questionnaires. You can do a lot of different things. And also, we have a wizard tool that helps you find your context-specific evaluation measures. So in whatever context you are right now, you can type it in. It will give you a recommendation what kind of user research and user involvement measures you can use. And with this, we hope to, together with the CYBATHLON's endeavors, also support human-centered design practices, of course. And this leads me already to the end of my parts. So I would like to thank you guys for the attention, of course, then also for a couple of questions afterwards. That would be great. Check out the Relab where you find all that information, all this research. And if you want to reach out to me, we can connect over LinkedIn. And now moving to Max Erick, we have yet another question, which is how can we now keep the human-centered focus in the technological implementation? So Max Erick, you will give us some answers to that.
Thank you very much, Jan. Thank you for this very nice segue also. And yeah, I want to answer now to you, what are technologies and also what are methodologies that will facilitate user-centered design? And so the question is not only how do I get a technology portfolio, but how do I get there fast? Because we have seen we have the translation gap. And as a matter of fact, it is also due to probably underestimating the complexity of the problem, as has been said already by Jan. About myself, the things you have not yet heard is that, yeah, I am an enthusiast of radio frequency, of optics, of mechatronics, of interdisciplinarity, especially also about medical technology. I myself come from a family which is populated with doctors. I'm one of the few renegades who is doing engineering. My job as a technology transfer manager is actually to connect people, to connect technologies to our company, to connect people of our company to our company, to help also support your teams. And by this also knowing what is lacking also in our company, how can we help you better with future products? One thing I'm also doing from time to time is I'm getting my fingers dirty. So for example, this project here was a collaboration with antibiotics, and I've learned a lot in this collaboration with antibiotics also. And we will be learning some of the lessons which I've learned also in that collaboration here. In my spare time, I'm doing music, I'm doing photography, I'm doing table tennis. I have a passion for science, I have a passion for a lot of things, and well. Now, without further ado, let's go for a simple thing. We have a lot of products, and the choice of the products may be overwhelming to you. Most people have already seen that slide. Probably what perhaps many people are not aware of is that we have also acquired a company called Parvalux, and it's doing very heavy motors, which could be, for example, useful in wheelchairs or where weight does not play a role, but where price does play a role. So if you want to have a lot of power for not too many dollars, that may be a way to go also. And we're very happy that we can also have them in our portfolio since then. Now, how can I save time in complex projects? Because you have seen there are a lot of motors, you have a lot of choices. How can I choose rightly? And the first thing is we have to be aware about the pilot tech gap, as we put it. And that's also something which I picked up from my colleague Jan. And it's not only about the teams teaming up with the pilot. I think that's the easy part. The question is, we are sitting here and we are covered by layers of abstraction to the pilots. So it's very difficult for us as industrials to talk to the pilots directly. But when we do so, it's very enlightening. So why don't we talk too often to pilots? What is happening here? First thing is the pilot has a user interface, if we want. Yeah, it could be a software user interface. So it's every gadget that he's using, everything, how it behaves, object recognition, intent detection, I don't know what. But then he has also a physical interface, which could be the adaptation mechanism. It could be the kinematics. It could be actors and sensors. And the actors are motors, gears, controllers, some other part also. And oftentimes, people have the impression you can solve with software what the physics could solve. Yeah, and so the question is, what can we solve with software? What can we solve with physics? But also the same thing here, kinematics. Good kinematics are often a prerequisite to really getting use of the actor. So where you place the actors actually can be even more important than the choice of the actor itself. And so at the end of the day, when you have done your design and you have done the design rounds of your scene, at the end of the day, you say, okay, I need a motor with so many Newton meters, and okay, that's okay. And you need not see the pilot anymore, which is a little bit of a shame. So I encourage everybody here who is listening to involve us also and to bridge the gap here so that we understand what is actually driving performance. And I want to encourage also you to think about your methodology, because what you would have thought is probably this kind of methodology, and this is already best of the art normally. So the first thing is you say, okay, understand your market, understand your customers. And so you make your questionnaires, you look at your market, you look also at the willingness to pay a certain price, because you cannot sell things which are just infinitely expensive. You boil everything down to clear specifications so that everybody knows what we're talking about, and you make sure that everybody has understood the same thing. And now you want to choose the appropriate technologies. And so I say, okay, I have a specification, but then how to solve it? You want to solve it with technologies that solve the task in the cheapest and most robust and most reliable way, and also in a safe way. Okay? And then you collaborate, because things are still complicated, and so you collaborate across your sites. And you also collaborate with the customer, you collaborate perhaps even with the suppliers, and then you're done. So that's a very good methodology, and that's what you would find in every average textbook about methodologies. And most people already forget those 4 steps, and so they jump directly into specifications, and that's already a catastrophe. So that methodology is a good one. But what happens if you don't know what you're doing? Because what we have looked at the moment was best practice. And there it's when you know what you're doing. And as we heard before, I think we are here in a country where we don't know what we're doing. We don't know what the customer is, so we don't know how a pilot is. We think we know what a disability is until, well, we find a pilot, or until somebody does an experiment, like, for example, injecting some liquid into your limbs, and then you don't feel anything anymore, and you're anesthetized, and then you find out how it is really to walk without, for example, feeling your ground reaction force. Okay. And so you will have to change your practice, because the worst things that can happen is if you're confused. That means that you are applying methodologies which are for clear projects and applying them to complex projects. If you do that, you will end up in infinite frustration, losing nerves, shedding tears, getting angry. And if you embrace the complexity, then you will say, okay, what do I do here? I have to have emergent practice. I have to do very quick experiments, as we have already seen a little bit with the design thinking approach. But we have to do that not only in the small team, we have to do that across the food chain, and that is super complicated. It could be even that you're in the chaotic place, because in CYBATHLON, we're often doing novel things nobody's ever tried out. So even trying out, you don't find out what you have tried out. And there you have to really accept that you're, in principle, although you may have a PhD, you may be a professor, but you're infinitely dumb. And once you have accepted that, it's very easy to get along. So if your expectations are very low, then the first thing is you start learning and you start becoming humble, and I think then the fun really starts. Okay. Also, you have to be then very open to the possibility of solving a problem in about 5 ways. Is it the software? Is it the hardware? Is it the user attachment? Is it the kinematics? What kind of solution do we really look for? And okay, so that means the first thing you do in a project which is complex or chaotic is you focus on the unknowns. And the first thing you have to do is to de-risk, 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 and de-risk. And you do fact-finding in your ecosystem. That's what we saw before. We had the pilots talking to the team. But you look, for example, also at academia, because in academia you will find a lot of resources. You might find resources with your peers. There might be also resources with the suppliers, because they have seen also a lot of stuff. And you may also want to talk to a core team of innovators, Not everybody is open to new experience. It's a character trait which is very difficult to change. And it's very frustrating if you have people in your team who are not open to new experience. So you will have a core team where like-minded people will meet and who are completely open to be challenged and who don't take it personally and who are happy to be challenged and who are thrilled by complex environments and say, okay, I thrive on chaos and I like that. Okay? Not everybody's business. Then what you want to do is you do simulation. And you do simulation already to eliminate errors. So to eliminate the obvious errors, you want to do analytical calculations, spreadsheets, matrix programs, digital twins, and you want to do hardware testing or part-time hardware testing. And then, if you're going to hardware, the next thing is you want to do minimum viable products. So that means something everybody else is joking about. And that's always innovation. Innovation is you start out with something which is really ridiculous. Yeah? And everybody else, your competitors will be saying, look at those guys. The trick is the first time your competitors laugh, the second time they say, and the third time they are shedding very hot tears. Yeah, that's the way you go. But you start with a really ugly product and you keep the expectations low. Then the other thing you want to do is you want to destroy your product. Yeah, so you do hold and has. That means highly accelerated stress screening, where you find out where it could break, and then highly accelerated lifetime tests, where you shake your product and break it. So like in this here, for example, you do temperature shock tests, whatever you think your environment will bring to your guy. So if it's an outdoor equipment, you want to go to saltwater tests and you want to do immersion tests and whatever you want to do, you want to find out your errors as soon as possible and redesign if necessary. What is also important is that you do smart communications. And there's so much more to be said about this methodology, but these are, let's say, the key takeaways for you as small teams. The first thing is communication is not everybody to everything everywhere. You start with very frequent communication here on the top, and it goes down in frequency to the below here. So you have a core team that wants to meet regularly, let's say 2 to 3 times per week. Otherwise, people will lose focus. Okay? And I want really to encourage that the core team meets regularly so that you stay relevant and everybody is talking same language because everybody thinks he agrees. And I like very much this graph. You even think you have involved the guy, but you didn't involve him in the technical phase. And so for that reason, the core team has to meet also with the pilot together 2 to 3 times a week. Then interdisciplinary negotiation in an interdisciplinary core team, which we said consists of people who are open to new experiences. For example, where do I put my inertia? Yeah. How can I perhaps make something lightweight? But if it's lightweight, perhaps there's compliance. Compliance may be a good thing, especially if you have patients who may hurt, if things are too stiff. But then the question is, what is eigenfrequencies? Can we still regulate that? What is the energy management of the whole system? Where do I put my batteries? And how can I recover energy, which is negative energy? And also the question about machine learning versus mechanical intelligence, software tuning of parameters, for example, impedance control versus real-time impedance control with variable stiffness actuators. So the question is really, you can solve problems in a multiplicity of ways. What is the best way? And that should be really negotiated with an open mind. Then you will have specifications which are tracked by the customer. And so I would say what we did, for example, with antibiotics, which was very good, is that we had a requirement specification document, which was super short, and some justifications for the people who wanted to ask the questions. But those who don't want to be bothered with technical details just get the requirements, and those who want to deep dive, they get the justifications and the calculations why they came to that. And the goal is here really readability. So there is also this kind of school where you have specifications which are 18,000 points of what you call properties, Sachmerkmale in German, which nobody ever reads, or only some quality engineers read. That's also important, especially if you are going to the purchasing department. They have to know what to purchase. But for the core team, you need something which is readable, which is discussable. So in Popper's sense, to be as clear as possible, so that you can also be refuted as clear as possible, that you can learn as fast as possible. Okay. And then at the end, you have a supplier tracked specification on compliance metrics, and that's the lowest thing here. So you don't change that every 2 days, because otherwise the team will get mad. Yeah, so you built in the filter. Here you can discuss everything and everything is allowed, but then you boil it down a little bit more, and here you are at a point where you say, okay, every 3 to 6 months you may change 2 or 3 items. Okay, and then everybody's happy, I think. So the people who are process guys are happy, and you need the process guys, but also the innovative guys are happy, and then that keeps things going smooth. Okay, now my takeaway now to the technology. What are the drivers for your user experience? And I will be focusing only on 3 things. There are many more things to say, but I want to give you the maximum, if you want, bang for your buck, for your valuable time. And I'm focusing on things which software cannot solve. So software cannot deal with friction, and everything else is a fairy tale. Software cannot compensate for inertia, and I will come back to that, why it's the case. Yeah? And software cannot, in principle, make up for dumb kinematics. So you will need smart kinematics. And we saw that already in the previous talk that, if you have 5 or 6 degrees of freedom, normally you have a lot of weight, and a lot of weight means poor performance, and no software can get rid of the weight. And so what happens is then these teams who have too many actuators end up finishing last, and that would be really a shame. So the question is, how can we do that in a smart way so that we don't waste too much weight? Okay. So, let's say, recap from last lecture, efficiency is a key factor. So efficiency means that, in principle, you want to be in that region above 90%, probably 95% for your gears or for your ball screws. You don't want to be in this wave-generating gears here. You don't want to be there. You don't need those gears. And you see that there is a factor of 4 or of 3 to 4 between good gears and bad gears for typical robotics energy consumption. Yeah, it's not the efficiency, it's not just some percent more. And for that reason, I think you should focus there. There's another motivation, and that's for the user experience. Gear in transparency starts really kicking in at 85%, and then things become really arbitrary because you put a certain current to your motor, and it could be something like this here, or it could be something like this here, and so you essentially don't know what you're doing. And that's a user experience where you say, yeah, it feels awkward, and it doesn't do what I want, and I don't get good feedback. It doesn't feel, it feels completely unhaptic, and I don't know what I'm doing here. And so for that reason, you could use needle-bearing gears, so for example, RUP gears, ultra-precision gears. You could use also dynamic torque motors. Those are motors which we especially designed for robotics, which are a good compromise between torque density, but also very low friction and very low cogging. Because cogging also in a user experience is something really weird. Cogging would mean that you have there's this kind of movement, which really doesn't feel like user experience. Yeah. Okay, and then motor inertia is something which software cannot deal with. For that reason, put motor inertia as much down as possible. It means low mechanical time constant. Then also, some people say, yeah, but I need to use this inefficient gear because it offers me low backlash or 0 backlash. The problem being that as soon as you're in a natural system, and a natural system consists of friction and elasticity, oftentimes you end up that the real elasticity that you get, the real hysteresis you get, is dominated by frictions times elasticity. So it's not at all clear that a so-called play-free gear really is play-free. In the real system, the friction uncertainty will generate a real-time hysteresis which can be in excess of a normal gear. And why inertia hurts and why there's no software is because of a very, very deep mathematical conspiracy, which is called Kramers chronic relations. And these are there. And as long as we're in causal systems, so that means a system which has a step response at t greater than 0, yeah, a system that doesn't know things in advance, then we have to say, okay, there are things about phases, there are things about amplitudes, and since a control system should have something like less than 180-degree phase, because otherwise you will have feedback, so you don't want to oscillate, then in principle you are limited in your control frequencies, you are limited in the performance of your software. And without going too much into details, because the mathematical theory to that is super difficult, but let's say, okay, let's analyze the impedance of a very simple control loop. Also here, without going too much into detail, you find out after some, a little bit of gymnastics that you get this impedance out. And let's now decompose the impedance. S, by the way, means here is the Laplace domain, so it means differentiation. And so 1 over S would be something else. Okay. And now we see that the output impedance is something like the inertia of the motor, then some proportional term, which you set in your control loop, and some differential term, which is a damper. And what you see is in principle here that the control system takes the motor, because that was the initial impedance, and adds its own term, but it cannot change that term. That's the point here. It cannot change that term. It adds this term, it adds this term, and it adds an integration term, which is physically not so easy to explain. But now the question is, how can I deal with this inertia? Because, as we see, the control system cannot change the inertia of the system. What do we do here? So if we look at the Bode plot, we can say, okay, here the D term kicks in at lower frequencies, the P term at even lower frequencies, so that's the spring term which you have with the proportionality of the PID control. The I term is at super low frequencies, but the motor inertia at high frequencies is kind of like fate. You just have the inertia that you have. So how can I deal with bad inertia? So the first thing is, as we said, you get to a motor with a very low mechanical time constant. But if you cannot do that, you could use, if you want, a negative D squared term. And I would always say, don't try this at home. But if you want to try it out, it's really fun. Do a negative D squared controller. If you don't believe me, it's really fun. I've done that also. You have to do that once in your life. The other thing is that you measure acceleration directly, and that would mean that you use gyros, or you use acceleration sensors, you use IMUs. That can help a little bit, but the problem is that those sensors also have delays. But that's a good approach, and with this, you can get rid of some of the inertia. Or the best thing is you add an elastic element. As every human is constructed, we have skin, we have muscles, we have everything else. We have interfaces to a physical environment so that we really don't hurt ourselves. Okay? And also recap here is, you can solve the problems in kinematics. As we said before, we have this whole chain, and we can use springs for the known part of the problem. So if somebody's walking and okay, here's its average weight, okay, you add a spring to the whole system, and perhaps the spring takes care of stuff. And then the motors need to weigh less. And as we have heard, weight of the motor is a performance killer. So do everything to do what you can not know, what you already know, to not do that with motors, but with springs. So use dumb element for dumb tasks and only use smart elements for smart tasks. You can use resonators, you can use lightweight designs, you can use tendons. That's very good at humans. You see everywhere, that you have the tendons, you have the actuation always where the human is not. Yeah? So you have here, you have the muscles, and here you have the actuation, and most robots are constructed as if the muscles were directly at the hand, and then you ask yourself why they don't perform. And as we said, okay, motor with a low mechanical time constant and efficient gears. And also in the same vein, belt drives, ball screws, what they like. Everything which transmits torque very efficiently is okay. And now, saying, okay, we want to bridge the gap between the motors here and the pilot or the UI or the team. We have the Young Engineers program, which will help you that. And it's a sponsoring program for your projects, but it's not about the sponsoring, actually. For us, it's about getting to know you, helping you, supporting you, and finding together the best solution, which may not be as obvious as you may think. And so for that reason, you can take part with this link, which is supplied here, is also supplied in the previous talk, so I don't want to go too much into that. And your take-home message is, methodology will save time if you manage your expectations, if you know which country you're in, if you know what you don't know. Then they're helpers for user experience. At least from a technological side, it's low friction, low inertia, and smart kinematics. And please involve your value chain. And that means from customers to suppliers to everybody else. Put them into one boat, at least those who are willing, and then await better results than the last time, hopefully. And I wish you all the best for your competitions and CYBATHLON and to bridge the gap of usability. Thank you very much.
Great. So thank you very much to Jan and Max Erick for this very interesting talks. And we're very excited to hear about your questions now. So if you have any, either text them on Zoom or raise your hand here.
So maybe I start with a very general question. If I ask you, Max Erick and Jan, if you look back at your research or your interaction with the teams or with end users, was there any specific feedback that you have still in mind that maybe changed your way of thinking when you proceeded in your career?
Mm-hmm. I can start. So for me, a very important and interesting moment was actually a negative moment, right? Because we always remember the negative moments a bit better. But actually, I worked on the physical attachment system, which aims to hold the user in place while all the motors that Max Erick just talked about do their magic, basically, right? And for such that this force transmission actually works well, the user has to be very fixated into a lower limb exoskeleton. And for the Varileg, we were working on different attachment systems, and I tried to be very innovative and be very sleek and try something new. And then, coming from the health science side, maybe not looking into engineering enough. So we had like a failure of a system with the pilot in it. And also we tested it with we always tested all our prototypes before on myself or on neurologically intact colleagues. But yeah, you cannot, and I think this is something that's the main take-home message, is like, you cannot pretend like you have a certain disability, or you cannot really understand how the body behaves when a paraplegic person stands on its legs, right? And we tried to simulate that, but it didn't work. So we had a failure of a system, which luckily nothing happened. There was no harm, but it was interesting to see that we tried our best to have the safety and everything ready and to simulate all the different scenarios. But at the end of the day, you have to be risk, right? So make sure it's very solid, and then start maybe decreasing weight at some point. But first of all, I think it needs to be bulky and safe.
Mm-hmm. Yeah, from my side, the first time I saw a pilot, it was so very different from what I thought. Okay, everybody has seen a pilot, but what I mean is really working together with a team to debug his device. Yeah. So that was something, because at the end you see the films and everybody is perfect, the CYBATHLON, everybody's happy, but the way there is much dirtier than everybody imagines, except if you have seen it. Yeah. And so that was my personal experience. Now, what kind of dirt can you actually avoid? I think two things are completely underestimated. The first thing is that human beings have an extreme ability to deliver very high torques in very short time in case of emergency. So if you trip, you have normally 10 to 20 times more torque than you normally get used to. And it's very difficult to access the torque directly from your brain, but it's rather reflex driven. So this is kind of a firmware selected torque. Yeah. And so my take-home message here is give enough headrooms for your motors, because what I've seen also is that people then are there and there's a little bit of over torque because there was a slight surprise and the motor already trips, and then the poor user is then falling down or being caught up by some kind of safety system. So give headroom for torque, but we speak here about peak torque, not continuous torque. So continuous torque can remain, but give headroom for your currents, give headroom for everything else. Well, you give headroom to your currents. What happens next? The currents are very high, and unfortunately, electrical engineers know that power is transmitted outside the cables. So all currents will be visible everywhere, which means you have humongous EMC problems, electromagnetic compatibility problems. So my thing is, if you're a mechanical engineer, please double check with an electrical engineer. Look, here's my wiring. What do you think? Is that okay? Do we need some shielding? Things like that. This can save a lot of headaches if you do that in time.
Great. Thanks a lot for your extensive answers. Very interesting to hear your point of view. Are there more questions from Zoom?
At the moment, not. You're still time to use the Q&A function. It's not the chat function. It's the Q&A function you need to use. Maybe another question to Jan from my side. You mentioned also that you discussed for the Varilek team the tactics of CYBATHLON, that you want to skip tasks. How much was the pilot involved there? Because at CYBATHLON you need to solve the task, but you can also score points if you do not solve all the tasks. So what did you discuss there with the pilot?
I think it's two things we have to separate. So one, of course, the CYBATHLON pilots are always usually very competitive people, right? So it's a challenge. So obviously they also would like to win if possible, and your chance of winning are the best if you solve all the tasks and are the fastest. So I think by purely asking the pilots which tasks do you want to solve and which you don't, I think the answer will be very easy, because I want to do all of them. But in Varilek, for example, a very specific example is the fact that you have to walk up and down a stairwell. Well, at least I think it's still the same. Yeah. And this, it seems very trivial, but if you ever worn an exoskeleton, it's a scary situation to be in. And there, for example, fears kick in and these kind of things, and you have to maybe approach from an easier level. And then if you feel like, and if you have all the confidence and you have full control, you can see if you want to solve all the tasks. But I think that's not necessarily even just a technical decision. It's often also what the pilot wants to try out and do. I do believe on the spec side, most of the teams try to go for solving all of them, except maybe for the hand discipline, where maybe you don't want to, don't have any feedback answers, etc. But I am not an expert of that discipline too much.
Is there anything you would like to add to that?
That's okay.
Okay, great.
Maybe another question to Max Erick. You were almost emotional when you talked about the best practice slide, where you had this chaotic approach, etc. So how much do you, or how often do you experience best practice when you work in daily life, also with customers? And what would you maybe recommend as one message to your collaborators as well?
Yeah. So I think best practice is called best practice because it's best. And that means if you're taking the very famous and overly used already analogy of the supertanker and the fast speedboat, then you would say the supertanker is super efficient in getting along very large distances. And so there you use best practices. You have clearly defined specs. You don't change the specs. You don't change the running system. Everything is greased and everything is running. So that's standard operations. And sometime you want to transfer what you're having into that system. So there's not a question about speedboat or supertanker. It's rather how do we transfer from the speedboat to the supertanker. The problems arise when you should be running a speedboat, but you try to put your supertanker into some kind of weird territory which you have never known. And supertankers are really, really bad at exploring unknown territories because they have really very slow acceleration, and the damage to be done is much greater. So I would say unknown territories, as we said, if we don't know what you're doing, change your methodology. And don't try to say, okay, it has worked 200 times in the last time, and so it must work here, and this is our process. Don't insist on your processes in this kind of projects. Yeah.
We have one. We have one. We have one question from the audience. It relates to what you, Max Erick, said. I tried to phrase it. Not sure if I got it right. So we were talking about the degrees of freedom, and the question was. You made a statement, I cannot remember, but you made a statement on the degrees of freedom. This time in the CYBATHLON exoskeleton race, you have to balance without crutches. So would you recommend to reduce the degrees or not increase the degrees of freedom because you have this specific task to make the system simpler. That's what I understand from the question. You made a statement regarding that point.
Yeah. I think it's a dilemma here. It's a conundrum, and the conundrum was well articulated by you also, that degrees of freedom in principle are a luxury because you need it. And if you want to do real task in real environment, then low degrees of freedom, which are only specialized to a certain task, may not help. The question is then, how can I get the degrees of freedom without wasting too much weight? And then you may want to invest in where to put really motors. Does a knee motor need to be at the knee? Or can it be here at the hip? And does the knee motor need to be a big motor, or do you need only peak torque, and can you deliver that with a small motor and, for example, with some other kind of transmission mechanism? So here I think that the whole question is about being smart in the kinematics, and the third question was also here, like in the old Makepa designs, where you really then can also have a spring. I think it can be overly complicated, but today I think there is also software where you can design springs in a smarter way, and perhaps that may help. I think so. Do everything to get rid of the tasks for the motor, and then use the motors for the right tasks, but then use more motors and with more degrees of freedom. Because otherwise, if you cannot use crutches, then I would say, then people can get quite, there can be angst, there can be total fear, because if you trip, you really want to extract torque in the moment when you're tripping. So I don't see any way out of the DOF conundrum here, except for smart design. Yeah.
Thanks.
Great, so thanks a lot for all your questions, and thanks again for being here today. Just as we already learned today, it's important to not only have effective solutions, but also simple solutions, and finding the right complexity in your designs. And if you want to learn more about that, we have a talk on the 13th of October with Heike, and she will tell you more about that. So be here.
Thanks for having us.
Thanks for having us, yeah. Thanks for tuning in.